Hello everyone, welcome back to our PySpark interview prep series. Today we're exploring a fundamental concept in distributed data processing partitioning in PySpark. Have you ever wondered how PySpark efficiently distributes data across a cluster to enable parallel processing? In this video, we'll break down what partitioning is, why it's essential for performance, and how it impacts data processing in PySpark. Introduction. In PySpark, partitioning refers to the process of dividing a large dataset into smaller, manageable segments known as partitions, which are distributed across multiple nodes in a cluster. Each partition contains a subset of the data and can be processed independently, allowing Spark to perform parallel processing across different nodes. Partitioning is essential in distributed data processing because it impacts the performance, efficiency, and scalability of Spark applications. When data is well partitioned, Spark can balance the workload more effectively across the cluster, maximizing resource utilization and reducing bottlenecks. Partitioning also minimizes data shuffling during operations like joins, aggregations, and sorts, which can be costly in terms of network and memory usage. Effective partitioning enables faster data processing, reduces latency, and improves overall system efficiency, making it a key optimization strategy for big data applications in PySpark. How partitioning works in PySpark. Initial partitioning. When you load data into PySpark from an external source, such as HDFS S3 or a local file system, Spark automatically partitions the data based on the properties of the data source and the available resources in the cluster, like nodes and executors. This process is known as initial partitioning. By default, Spark will decide the number of partitions to create, but you can control this by specifying an unpartitions parameter during data loading. Setting the number of partitions can help balance the workload across the cluster, improving parallelism and resource utilization. For instance, in dfspark.read.csv path, numPartitions 5, the data is loaded into 5 partitions, which can then be processed independently across Spark's worker nodes. Repartitioning. Repartitioning is a method you can use to increase or decrease the number of partitions in a dataset. The repartition method, which involves data shuffling, redistributes data across the partitions, creating a more balanced distribution. While shuffling can be resource intensive, repartitioning is valuable for optimizing data distribution for tasks requiring parallel processing. For instance, if you have a dataset with an uneven load distribution, df.repartition10 will split the data into 10 partitions, helping Spark balance the workload evenly across tasks. Repartitioning is especially useful when preparing data for parallel processing to achieve better performance in large-scale computations. Coalescing. The coalesce method is another partitioning approach commonly used when reducing the number of partitions without a full shuffle. Coalescing is particularly useful for consolidating partitions, such as when you want to save data with fewer output files or minimize the memory footprint. Unlike repartition, coalescing minimizes data movement, making it more efficient for operations that do not require a perfectly even distribution across partitions. For example, df.coalesce5 reduces the number of partitions to 5, helping streamline the data for specific tasks like writing to storage without a costly shuffle operation. However, coalescing can lead to unevenly sized partitions because it doesn't fully redistribute data. Partitioning on specific columns. For operations like joins, aggregations, and group by, partitioning by specific columns referred to as partition keys can significantly improve performance. By partitioning data based on a specific column, Spark groups related data within the same partitions, which reduces the need for data shuffling during operations that rely on those columns. For example, if a dataset includes a department column and you frequently perform joins or aggregations based on department, using df.repartition department will optimize these operations by keeping department data together. This column-based partitioning allows Spark to access and process related data more efficiently, ultimately speeding up these compute-intensive operations. Types of partitioning in PySpark. Hash partitioning in PySpark. Hash partitioning is a commonly used partitioning method, distributes data based on a hash function applied to a specified partition key. This approach ensures that data is evenly spread across partitions by computing a hash for each record and assigning it to a partition based on this hash value. Hash partitioning is particularly effective for operations where balanced data distribution is crucial, such as joins or groupie operations. By ensuring that records with the same key are placed in the same partition, hash partitioning reduces the need for data shuffling, which can be a costly operation in terms of performance. This method is straightforward to implement in PySpark and is widely used for its efficiency and ability to maintain balanced workloads across Spark's distributed processing tasks. Range partitioning. Right? Range partitioning, while less common in PySpark, organizes data into partitions based on contiguous ranges of sorted values. In this approach, data is divided into specific ranges such as numeric or alphabetical ranges, allowing related data to be grouped together within the same partition. Range partitioning is especially useful for ordered operations or tasks requiring sorted data, as it enables efficient access to records within a certain range without scanning all partitions. However, implementing range partitioning can be more complex since it requires sorted data and careful range selection. In PySpark, range partitioning is not as widely used as hash partitioning, but it can be beneficial in specialized scenarios where ordered data processing is required. Despite its utility, range partitioning needs to be set up thoughtfully to ensure that partitions are well balanced and that data does not cluster heavily within certain ranges. Example 1, basic repartitioning to increase parallelism. In this example, we begin by setting up a Spark session with the application name partitioning example. This session initializes our PySpark environment and provides access to Spark's distributed data processing capabilities. We create a sample dataset consisting of employee names and their corresponding salaries. This dataset is replicated 1000 times to increase its size, allowing us to better demonstrate the effects of partitioning on parallelism in Spark. Next, we create a data frame from this dataset with two columns, name and salary. By default, Spark determines the initial number of partitions based on factors such as the size of the dataset and the configuration of the Spark cluster. To view this default partitioning, we use df.rdd.getNumPartitions, which provides the initial number of partitions for the data frame. The output here shows the starting number of partitions that Spark automatically assigned. For more effective parallelism, especially when working with larger data sets, it can be beneficial to adjust the number of partitions. We use the repartition method on the data frame to increase the number of partitions to 10, creating a new data frame df underscore repartition with this updated partition count. Increasing the number of partitions can help distribute the data more evenly across the cluster's nodes, allowing Spark to handle more tasks in parallel and improving processing speed for large workloads. After repartitioning, we check the new partition count using df underscore repartition.rdd.getNumPartitions, which confirms that the number of partitions has been successfully adjusted to 10. This example demonstrates how repartitioning can improve parallelism in Spark by increasing the number of partitions, optimizing data distribution across nodes, and enabling Spark to process tasks concurrently with greater efficiency. Example 2, partitioning by column to optimize joins and groupie operations. In this example, we start by creating a data frame containing sample employee data, which includes the employee's name, department, and salary. This dataset gives us an opportunity to demonstrate how partitioning by a specific column, such as department, can optimize certain operations in PySpark. To improve performance for operations that involve grouping by department, we repartition the data frame by the department column using the repartition method, which by specifying department as the partition key, Spark reorganizes the data so that each partition contains records belonging to the same department. This approach is especially useful for operations like joins, aggregations, and group by, where grouping related data together within each partition can significantly reduce data shuffling and speed up execution. The repartition data frame df underscore partition now has data organized by department, which enhances efficiency for operations that process data by department. Following the repartitioning, we apply a groupie transformation on df underscore partition to count the number of employees in each department. Because the data is already partitioned by department, Spark can perform the grouping operation within each partition with minimal data movement, reducing overhead and improving performance. The count method provides the number of records in each group, and the show action displays the results in the console. This example illustrates how partitioning by a specific column in PySpark can optimize data processing. By grouping related data within each partition, we reduce the need for shuffling and enable Spark to perform operations like grouping more efficiently, ultimately speeding up data processing for large and distributed data sets. Example 3, coalescing to reduce the number of partitions for efficient output. Um, in this example, we create a data frame using a sample dataset containing employee names and salaries. To increase the size of the dataset, we replicate the records 1000 times, making it large enough to illustrate partition management in Spark. After creating the data frame, we check the initial number of partitions by calling df.rdd.getMPartitions. This output provides insight into the default partitioning Spark applies based on the data size and configuration, which is useful for understanding how Spark initially distributes data. To optimize storage and reduce the number of output files, we use the coalesce method to decrease the number of partitions in the data frame to 2. Unlike repartition, which involves a full shuffle to redistribute data evenly, coalesce minimizes data movement, making it a more efficient option for reducing partitions, especially after filtering or transformation operations. Coalescing is particularly beneficial when saving data as it reduces the number of partitions without the overhead of a full shuffle. In our example, df underscore coalesce df.coalesce2 reduces the partitions to 2, enabling efficient data consolidation with minimal shuffling. Finally, we write the coalesce data frame to an output folder in CSV format using write.mode override.csv output underscore folder. This action saves the data in a single directory with fewer files, which can simplify data management and improve read performance for subsequent tasks. By coalescing before saving, we reduce storage costs and improve the efficiency of downstream operations that need to read the output data. This example demonstrates how coalesce can be an effective tool for partition reduction and optimized data storage in PySpark. And that wraps up our discussion on partitioning in PySpark. We've covered why partitioning is so important for distributed data processing and how it helps optimize performance by enabling parallelism and minimizing data shuffling. If this video helped clarify partitioning for you, please give it a thumbs up, subscribe for more PySpark content, and hit the notification bell to stay updated on our latest videos. Thanks for watching and see you in the next one.